Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. Welcome back to MDA 3053 Introduction to Machine Learning. I'm Dr. Maharani Abu Bakar, is the instructor of this course. Today, we will explore a powerful unsupervised learning method called Principal Component Analysis or PCA. This technique is widely used for dimensionality reduction, helping us manage large data sets by reducing the number of variables while retaining essential information. Let's begin. Here is the overview of today's lecture. We will cover the following key topics. So first, what is dimensionality reduction and why is it important? And then understanding the key steps in PCA including standardization, covariance matrix, eigenvalues, and eigenvectors. We'll also go through examples and highlight the practical application of PCA. Let's begin with the concept of dimensionality reduction. So dimensionality reduction is a technique that reduces the number of input variables in a dataset. So imagine we have a tracking multiple features like brand, and then the region, type, and then type of part, and then time of year, and then pricing, right? So maybe 5 or more variables. However, by analyzing correlation among these variables, we might find that only 3 of them are strongly predictive of sales. So this one is, for instance, the sales, right? So among these 5 variables, we might just need 3 variables that really influence to the predictions of sales. So we can reduce from 5 dimensions to 3 dimensions. So simplifying the model without losing key information. Let's look at another example involving economic forecasting. So suppose we want to predict the GDP of the United States in 2024, right? And we might collect hundreds of features such as US GDP from the first quarter until nowadays, okay? And then we also have economic indicators such as employment rates, inflation rates, right? And then we also did some census data, okay, from 2010 about the number of Americans who work in each industry. And then we also gather stock price data, Bitcoin, and so on. In other words, we have a lot of variables that need to consider. But the question is, we really need all of these variables? Okay? Or maybe we reduce the question, amongst these features, which one that really influence the prediction of the stock price, for instance? Okay? So this is where dimensionality reduction becomes essential to identify the most significant patterns in the data while removing irrelevant or repetitive features. So when we reduce dimension of the feature space, we simplify our model. Fewer features means fewer relationships to analyze, okay, and less risk of overfitting and lower computational costs. So there are two primary strategies. So first, feature elimination, and the second one, feature extraction. So feature elimination means we reduce the feature space by eliminating features, okay? And then feature extractions means we create new independent variables where each new independent variable is combination between each of the old independent variables. Okay. So why is dimensionality reduction useful? So these are some advantages of dimensionality reduction. Okay, first, less compositional time, definitely. So it will our model will be trained faster. Okay, and then remove redundancy of similarity of data sets. Okay, so this one is done by eliminating similar features, and then it saves storage space where we just need fewer variable to store, right? And then easier to visualize, definitely, because we reduce the dimension, then easily we will easily visualize it, right? And then improve the interpretability. So it once will help us to focus on the most significant features. And in many cases, this one also improves the model performance. Now, let's move on to the principal component analysis. So PCA is widely used feature extraction technique that reduces the number of input variables in a dataset while preserving as much as variability as possible. It does this by transforming the original variables into a new dataset of uncorrelated variables called principal components. As can be seen in this illustration, so for instance, we have complex data sets with lot of variables here, and then under PCA we can reduce the variables, okay, into the reduced variables. So how does PCA works? So it finds the direction where the data varies the most and projects data along those directions. These directions are defined by eigenvectors, and the amount of variance captured in each direction is represented by eigenvalues. So the first principal component captures the most variation, the second captures the next most, and so on. Alright, now we move to the some steps in the PCA. So the first step in PCA is called standardization. Okay, so standardizations is where we transform the variables, various variation of variables into the same standard. All right. So, for instance, maybe variables measured in different units or scales. For example, income in thousands and percentage unemployment. So they have different scales. So we need to make certain standardization for them. So for this, in this case, we use the formula that is called this one. Wait a minute. So z equals to variable values subtract with means divided by standard deviation. Okay, where means, so we can find the standard formula of means. Okay, and then this is the standard deviations formula as normal in the statistical methods. All right, and yeah, so this is the formula for doing standardization. Okay. In the next steps, we compute the covariance matrix. So what is covariance matrix in this case? So covariance matrix shows how much each variable varies with every other variables. Okay, so it is a square symmetric matrix where the diagonal elements represents the variance of individual variables, and the off-diagonal elements represent the covariance between different pairs of variables. So as can be seen here, so this is the covariance matrix, right? And this is the formula for the covariance itself, right? So here we discuss the some interpretation for the covariance itself. Okay, as it can be seen here, as can be seen here. So if the value of the covariance matrix is positive, then it indicates that the variables are correlated. Right? If the value of the covariance matrix is negative, then it indicates that the variables are inversely correlated. Now comes to the most important mathematical steps. Yeah, so we compute the eigenvectors and eigenvalues of the covariance matrix. So each eigenvector defines a principal direction, and each eigenvalue tells us how much variance lies along that direction. Right? So at first principal component corresponds to the largest eigenvalue, where this is the direction with the most information. And then we sort the eigenvalues in descending order and retain the top k components based on how much cumulative variance we want to preserve. Alright, so finally, now we construct the feature vectors after we compute eigenvalue and eigenvectors. So this is a matrix whose columns are the eigenvectors corresponding to the principal component that we have selected. And then we project our original data onto this lower dimensional space, where this gives us the transformed data set. Now with fewer variables but preserved structure. Alright, that's end of part 1 of our discussion on the PCA. And we will continue for the part 2 in the next video.